Thank you very much for this opportunity to present our research on cost and quality of additively manufactured metallic parts. I am especially excited to show our results that models can be very useful to address both these issues. And many of these models are really very easy to build and very easy to use. So anyone that wants to use them can actually do so. Here's the outline. First, I want to share some facts about cost for the established products. That means products that are mostly free of defects. But defects are also very common in additively manufactured parts. So I want to give two examples of model-based dimensionless analysis, one for reducing distortion, the other one for reducing surface roughness. And then I want to discuss two applications of physics-based mechanistic models for reducing lack of fusion and for controlling grain structure. And finally, many of the real problems are what we call inverse problems. That means we may like a certain attribute, and can the models tell us what process parameters we need in order to get a particular attribute in the final part that we are making. So I'm going to give one example of that. For metal printing, both the feedstock and the machines are quite expensive. So it is fair to ask if the additively manufactured parts can be cost effective. And we asked that question several years ago, and we did a survey of the usage of printed parts in various industries ranging from consumer products to automotive, to healthcare, to energy, to aerospace and marine industries. And we found that parts made by additive manufacturing are widely used in all of these industries, and the different numbers here show the revenue share of the additively manufactured parts in those industries. On the right, we have the Boeing 787 Dreamliner, which is the most fuel-efficient twin-engine jet airlines that can carry several hundred passengers depending on the specific model. And it uses several 3D printed components. And other aerospace companies are also using 3D printed parts. So additive is cost competitive in many industries. This figure shows the cost per item for the manufacture of a landing gear part made by die casting and also by additive manufacturing, specifically by powder bed fusion process. For die casting, the initial cost is high because the setup and the tooling cost for die casting, but as more parts are made, the cost per item comes down because those initial costs are distributed among many parts that are made. In case of additive manufacturing, it does not have any tooling or setup cost, and therefore the cost per item does not change significantly with the number of items made. So depending on the number of parts made, additive manufacturing can have a big advantage in terms of cost. This figure shows the cost of the material as a part of the total cost for the printing of various materials. The data show that the material cost is important, but it is not the dominant cost. The cost of the machine time and post-processing are more important. Here's a breakdown of the various costs for the printing of a stainless steel bottle opener. This is a complex design and it needs a support structure shown here for printing. So both the cost of making this support structure as well as removing the support structure after the part is printed add to the cost. Now, if the part is so complex that it cannot be made by any other means, then the high cost may be justified. Similarly, reducing part count or part weight can also offset product cost. Defects are very common in additive manufacturing. For example, there can be cracking, lack of fusion, residual stress and distortion, and in extreme cases, parts can be separated from the base plate, so there can be delamination, and also many of the alloys contain volatile components, and at high temperature they can be selectively vaporized so that the composition of the final part may be different from the composition of the initial feedstock. In this case, we are showing printing of a titanium 6 aluminum 4 vanadium part in which aluminum has been selectively vaporized so that its composition is much lower than that in the feedstock material. There can be balling on the surface, or the surface can be simply very rough. And also during solidification, we can form long columnar grains that are detrimental to mechanical properties. The microstructure may have brittle phases, or the microstructure may have porosity. So all of these defects have to be mitigated while a new part is being developed. And because the cost of the machine and the cost of the feedstock are pretty high, we cannot do trial and error testing that we can do with conventional manufacturing. So models provide a very good solution because they are based on scientific principles and they require a minimum amount of testing. So I'm going to give you two examples of models to avoid distortion and surface roughness. Distortion is very common because of rapid heating and cooling, and important variables that affect the distortion include process variables such as power, speed, powder feed rate, and deposition time, and also material properties such as density, rigidity of the material, and other parameters affect the extent of distortion. So our goal is to express maximum strain as a function of process variables and material properties. To build a model for thermal distortion, we use scaling analysis based on Buckingham Pi theorem. The important variables are listed here. Volume expansion is the product of volumetric thermal expansion coefficient multiplied by temperature change, heat input per unit length. If the heat input is large or if the volume expansion is large, the part will be more susceptible to distortion. Similarly, if the total time taken is large, the part will be more susceptible to distortion. Also, if the part is rigid, then it will oppose distortion. Higher density materials will also oppose distortion. And finally, Fourier number, which is the ratio of heat transported by stored. If the Fourier number is large, that means heat is transported quickly, and that will mean lower distortion. So when we combine all of these variables into non-dimensional terms, we get 3 pi terms, and when we combine all of them, we get an expression for the distortion or strain, maximum strain, which is proportional to beta times delta T, which signifies volume expansion and is proportional to heat input per unit length raised to the power 3 by 2. It's proportional to time, inversely proportional to EI, which represents rigidity, inversely proportional to F, which represents Fourier number, and inversely proportional to square root of density. So we are going to check how experimentally we can validate this expression. This plot shows that the strain is linearly proportional to heat input per unit length raised to the power 3 by 2 based on independent experimental data. Similarly, when we plot beta delta T and thermal strain, the thermal strain is also linearly related to beta delta T, as we would have expected based on the model that we developed. For a given set of process parameters, such as the ones given here, the temperature fields, the fusion zone dimensions, and the heating and cooling rates will depend on material properties. As a result, strains will be different for different parts made with different alloys, and this is what is shown here. Stainless steel 316, Ti 64, and Inconel 625, they show different extents of strain. It's also very important to validate the model with experimental data so that we can use the model with confidence. And this is what we are doing. We are plotting thermal strain versus the thermal strain parameter which our model gives, and we find that this expression describes the model very accurately for preventing distortion. We can use Buckingham Pi theorem to make a model for surface roughness. The important variables are listed here. High enthalpy of melting, whether or not it takes a lot of heat to melt the feedstock or not, is an important variable. If the layer thickness is high, then the surface is likely to be rough because of a staircase effect. High length to depth indicates an unstable pool, and therefore the surface could be rough because of that. Large contact angle will mean poor weighting, and therefore it can cause roughness. Low heat input may mean discontinuous pool, and the surface can be rough because of that. But Marangoni force, which distributes the liquid easily, if Marangoni force is large, then there will be uniform spreading of the liquid and the surface would be smoother. When we do a similar exercise, we can make a surface roughness index or SRI, which would depend on E, the enthalpy of melting, the layer thickness T square, the epsilon, which is pool length to depth ratio to the power 1/4, to square root of theta, which is the contact angle. H is heat input per unit length, and F in this case is the Marangoni force. And we can plot the SRI as a function of experimental data on these variables so that the model can be validated. Here we compare the computed surface roughness with the corresponding measured experimental values, and they seem to show a fair agreement with 126 independent experimental data. And these type of models, when they are validated, can be used to reduce roughness. We can use a similar methodology to build a model for lack of fusion defect. The final form is shown here, and the variables that are important are listed in this table. But in short, the lack of fusion defect is the ratio of the heat required to melt a unit volume of the feedstock divided by the energy supplied per unit volume multiplied by a Fourier number, and then this T is the layer thickness, D is the depth of penetration, H is the hatch spacing, and W is the width of the fusion zone. As you see, we will need the dimensions of the fusion zone in order to use this model. And those dimensions are obtained from a separate model. When we plot the lack of fusion index or lack of fusion number on the x-axis versus independent experimental data on void fraction, we see a linear trend. So the model can be validated with independent experimental data, and the use of the model would require the values of the fusion zone dimensions, and these have to be obtained from a separate independent model. The dimensions of the fusion zone are obtained from a model that is built by fitting data. The depth of the fusion zone divided by the radius of the beam is plotted on the y-axis, and on the x-axis we are plotting the normalized energy input. So what is that? Delta H here is the absorbed energy per unit volume, and Hs is the enthalpy of solid at the melting point. So when we have this value, delta H by Hs, we can then read off from the y-axis the depth of the fusion zone. Similarly, we can use another expression to obtain the width value of the fusion zone. And then we have our model for the lack of fusion number, so we can obtain the extent of lack of fusion using this model. A well-tested heat transfer and fluid flow model can calculate the fusion zone geometry in different hatches and different layers. And unmelted regions between the two consecutive tracks and layers, they indicate the lack of fusion defects. To make a fully dense part, there needs to be sufficient overlap among different adjacent hatches and layers. For a given alloy, higher power and slow scanning will result in larger fusion zones and less lack of fusion defects. And just the opposite will also happen. That means if the power is low and scanning speed is fast, then the fusion zone would be smaller in size and there is likely to be less overlap between adjacent hatches and between layers. And for a given set of process variables like it is given here, the thermophysical properties of the alloys determine the size of the fusion zone. And this is what we see here. In case of stainless steel 316, the fusion zone size is smaller than aluminum silicon 10 magnesium alloy. And so in case of stainless steel 316, for these processing conditions, there is going to be lack of fusion defects, and in case of aluminum silicon tin magnesium alloy, there is not going to be any lack of fusion defects. Heat transfer and fluid flow models can be very helpful in understanding the evolution of grain structure. This figure shows unidirectional scanning of a laser beam from left to right. So the melt pool looks like this. The isotherms are compressed ahead of the beam and expanded behind the beam near the trailing edge. The primary heat flow direction is perpendicular to the surface of the fusion zone. This is also the direction of the growth of the primary dendrites. So the primary dendrites grow at an angle that is about 60 degrees with the scanning direction, and that is what we see in the calculations as well as in the experimental results. Scanning pattern, one that alternates in progressive layers. That means in the first layer, the beam goes from left to right, and in the next layer, the scanning direction is reversed. So it goes in the opposite direction from right to left. So that is what we see here. The primary heat flow direction changes at 90 degrees. And that is also one can see from perpendicular to this surface as opposed to perpendicular from that surface in the second layer. And so the heat flow directions would be very different in different layers. Experimentally, what we see is that the growth directions of primary dendrites are at 90 degrees with each other. In each layer, the primary dendrites grow perpendicular to that of the previous layer. So there is a mismatch between the primary dendrite growth direction and the heat flow direction. And the heat flow direction is 60 degrees with the scanning direction, but the primary dendrite growth direction is about 45 degrees with the scanning direction. So let us examine why that is so. If the primary dendrites grew along the dominant heat flow direction, then this would be the solidification pattern, and the grains in different layers would be aligned to this pattern. But that is not what happens. If the primary dendrites followed the 60-degree pattern with the scanning direction, then it would have followed this path, the solidification path too. But that does not happen. The data are consistent with solidification pattern 3 shown here, where the primary dendrites grew from the secondary dendrites of the previous layers. The secondary dendrite of this layer is perpendicular to that layer, and that's where the primary dendrites of the next layer grows. And the growth pattern is zigzag in adjacent layers. It shows how the growth patterns can be adjusted by changing the scanning pattern. So far, we have seen that both the scaling analysis using non-dimensional numbers as well as mechanistic models can be very useful to control defects as well as solidification patterns. But in many models, such as heat transfer and fluid flow model, one provides the process parameters and thermophysical properties of the alloys as input and calculates temperature and velocity fields, fusion zone geometry, cooling rates, and other attributes of the welds. or other attributes of the fusion zone. But what if we want to compute the process variables needed to obtain a specific attribute? For example, I need to obtain a specific fusion zone geometry, whether it is for welding or additive manufacturing. Can the models help us to do that? And this is the classical inverse problem. In most problems of this type, there can be multiple solutions. In other words, if I specified the fusion zone geometry, there would be different sets of variables that can produce that specified geometry. For example, if one is using an electric arc to melt a metal, there are many combinations of current, voltage, and scanning speed that would result in the specified fusion zone geometry. So let's take an example. In our forward model, we specify current, voltage, scanning speed, and other variables such as thermophysical properties to calculate fusion zone geometry. We can repeat this exercise many times by providing many different combinations of variables and check what kind of fusion zone geometry we are getting, whether we can get a match between what we want and what we calculate. If there is a mismatch, we can go back and redo this. Or we can construct a suitable objective function that will provide quantitatively a fit between what we seek and what we get. And in principle, we can do a bunch of calculations and find a suitable algorithm to search for the different combinations of current, voltage, speed, power distribution, and other variables that would give us the desired fusion zone geometry. I have a stainless steel 304 plate, and I do an experiment with certain conditions that are specified here, current, voltage, and welding speed, and I get a fusion zone whose half section looks like this. I want to know what other combinations of current, voltage, and scanning speed can result in this particular geometry of the fusion zone. So we start with a combination of many groups of current, voltage, and scanning speed, and we plot the objective function of the initial population of solutions as a function of current, voltage, and scanning speed. Here I am showing objective function as a function of current and voltage for the initial population. For some of the points, some of the combinations of variables, we have low objective function, and for other ones, I have high objective functions. We want to use a global search algorithm called a genetic algorithm, which adds and removes individual combinations of current, voltage, and scanning speed, and then recalculates the objective functions of the entire population. And after many of these iterations, we get 8 combinations of current, voltage, and scanning speed that would give us acceptable objective functions. That means acceptable values of current, voltage, and scanning speed that would result in low values of objective function. That means we are now getting for all of these combinations the right width of the fusion zone and the right depth of the fusion zone. And there are 8 alternative variables that can give us that. Each of these solutions give us the fusion zone geometry we want, which is written here. Penetration 1.23 millimeter and width would be 4.47 millimeter. And in each case, for different values of current, voltage, and scanning speed, we get more or less the same depth of penetration and same width. If we look at the values, current varies between 106 ampere and 167 ampere. The voltage varies from 9.8 volt to about 14.4 volt, quite a bit of variation. And the scanning speed ranges from 4.3 to 9.6 millimeter per second. But all of these combinations provide the similar penetration and width, almost the same value that we wanted. So we tested the calculations by conducting experiments. We take each of these cases, we physically do an experiment, and then look at the depth and the width of the tracks and compare them with our specified values. So we did experiments using the different combinations of current, voltage, and scanning speed. And for each condition, we obtained a depth of penetration and the width of the fusion zone similar to what our target was. So all of these different combinations of variables could give us the geometry. What we computed matches with experiments. We could get the target geometry of the fusion zone via 8 different combinations of current, voltage, and scanning speed. We can also specify another desirable attribute, such as the cooling rate at a given location, and compute multiple combinations of process variables to obtain the specified target cooling rate. This example shows how inverse modeling can tailor fusion zone geometry and other attributes of welding or additive manufacturing. For 3D printing, equipment and feedstock are expensive, but when the parts are largely defect-free, they are cost competitive for a wide variety of applications. Rapid movement of high power density heat source, powders and liquids, and repeated heating and cooling results in many types of defects in parts. Various types of models ranging from non-dimensional analysis to mechanistic models to complex reverse models are very helpful to improve cost competitiveness and quality consistency. Many models are delightfully simple. They do not require expensive facilities. They provide equal opportunity for everyone to contribute, and they make the world a better place and a more inclusive place.